Well, welcome to video 4 of chapter 2. This is on domes. I did a lot of dome design and we did a lot of dome building when I was in college at A&M in the early 70s. The geodesic dome was all the rage, and the father of the geodesic dome and math was the inventor of Buckminster Fuller, who also in the 1930s developed the first three-wheel minivan called the Dymaxion car. He later on invented the Dymaxion house, which was a prefab house that had all the amenities of a regular home. And he was quite an interesting fellow. Well, anyway, let's get into the dome. Ching defines in our book a dome is a spherical surface structure having a circular plane and constructed of stacked blocks. A continuous rigid material like reinforced concrete or of short linear elements, as in the case of a geodesic dome. A dome is similar to a rotated arch except that circumferential forces are developed that are compressive near the crown, which is the top of the dome. That's the crown. Um, where am I at? There we are. And tensile in the lower portion. You get more tensile forces down here, and especially down around the thrust ring at the bottom. Now, what else can you make a dome out of? What's an igloo made out of? It's made out of ice blocks, compressed snow, which is turned into ice, and it's a dome. So it can be made out of anything: masonry, ice blocks, um, sheets of plywood that are bent in a shape. So let's move on. The meridional forces acting, the meridional forces, meridional forces that are acting along a vertical section cut through the surface of the dome are always compressive under the full vertical load. These are the imaginary lines, force lines, going through the meridian of the dome. Okay. And then we have compressive and tensile stress hoop strength around here, trying to hold these meridional lines in place until we get to the bottom where we have the tensile thrust ring. Okay. So hoop forces or hoop stress restraining the outer plane of the movement of the meridional strips in the shell of a dome are compressive in the upper zone and they're tensile in the lower zone. You don't need to know this. You're not engineers. This just gives you some vocabulary for the dome. The transition from compressive hoop forces to tensile hoop forces occurs at an angle from about 45 degrees to 60 degrees from the vertical axis. That's not necessary for you to understand unless you're going to do dome engineering. A tension ring encircles the base of a dome to contain the outward components of the meridional forces in a concrete dome. This ring is thickened and reinforced to handle the bending stresses caused by the differentiating elastic deformations of the ring and shell. Now, there are different types of domes. There are the Schwindler domes, or steel dome structures having members that follow the lines of latitude and longitude, and a third set of diagonals completing the triangulation. You can see the little triangle there. Lattice domes are steel dome structures having members that follow the circles of latitude and two sets of diagonals forming a series of isosceles triangles. Now, the most common and mostly built of the geodetic structures are the geodesic domes. They're steel dome structures having members that follow three principal sets of great circles intersecting at 60 degrees, subdividing the dome surface into a series of equilateral spherical triangles. Now, when you get into dome mathematics, you talk about the frequency of the dome and such as that. However, most common of these are the geodetic structures. Now, the pluses, one of the big pluses for a dome structure, and I will put up some PowerPoints that you need to link on, are that it covers a large surface area with the least amount of material, and it's very economic, assuming you have the skilled labor that understands how to actually put one of these together. The disadvantages is, what do you do with a circle? I've got a square couch. What do I do with a circle? Now, another type of dome that over the years has become extremely popular is from the Monolithic Dome Institute. Stopper, who died in 2023, took the concept of the geodesic dome and expanded it. So we have a typical foundation here. We have a typical foundation. We have the airform. It's an airform. It's a giant balloon that's custom made, and we pump air in here with a blower, and it expands the airform. And we have reinforcing rebar over the foam. Okay. We have the first layer of urethane foam that is sprayed underneath the airform. There are rebar hangers that are put in here. We have a second layer of urethane foam that's sprayed over the first layer and the rebar hangers. And then we have reinforcing rebar that's tied to the hangers that poke through the layers of foam. And then we have shotcrete, which is sprayed concrete on the interior of the dome. So the interior of the dome is concrete. There's a sandwich of a high-tech urethane foam between it and the airform. The airform is a UV-resistant flexible form that stays in place. And some people paint them, or some people come in and spray an outer coating of shotcrete and then try to weatherproof and coat that. And there's the exterior coating over the airform as it's shown away there. So that's a cutaway of the modern monolithic domes. And some of these are huge. Schools, sports facilities, you can have a vertical ring wall, and the top is a dome. Storage facilities, these are used a lot in agricultural storage. Big ones, huge ones. In fact, there have been some fires in some of these, and the foam and the concrete have protected. These things have weathered raging fires, tornadoes, hurricanes. It's one of the huge advantages to a dome is that they're highly resistant to wind loading and tornado loading. And this is a safe room up in the Dallas area. If I'm not mistaken, it's up in the Dallas area where the community goes when there are tornadoes through Tornado Alley. Homes. They have a Dome Building Institute. This is up in Little Italy, Texas, which is off of I-35 in Texas. It's north of Waco and south of Dallas-Fort Worth area. These monolithic domes have been built all over the world. And there's Arnold Wilson, Dave South. I said Stopper. I digress. Anyway, he was a monolithic dome pioneer and an engineer. Okay, let's look at some houses. Okay, homes. Okay, there's one along South Carolina Beach. It's called the Dome Institute, the Monolithic Dome Institute. You can search this if you choose to. Now, what did I say about the floor plans? Let's look at some of the floor plans. That's a challenge for some people because you have in any dome, whether it's a monolithic or geodesic dome, I don't know too many round beds. So we have a square bed and we're sticking it in a round structure. You see these interior walls are typical interior walls. Okay. Some of these domes are 2 and 3 stories tall. So your floor plan can be a challenge. Some people like these. They're structurally sound as all get out, but they can be a challenge for interior layouts. And people had that problem when geodesic domes became very popular to construct and live in. I would like to have one myself, but I've always been stuck in subdivisions, and you can imagine taking a typical subdivision lot and trying to fit one of these in it. Thus, as we said during the site development, since your lots are basically rectangle, and cars are rectilinear, and garages are rectilinear, these can be a challenge to fit in a rectangular world. But again, they're structurally sound. These things have survived hurricanes and tornadoes where other conventional structures have been completely destroyed. I could not find the aftermath of the tornadoes that went up through Little Italy, Texas. They did an aerial photo of the post-tornado run several years ago, and the only structures standing were the monolithic domes. So that's enough of that. I can't go by without the Dimax. 1933.
Medium transport, because if just going to go on the ground, I knew people would call it an automobile. It wasn't designed just to be an automobile at all. She was so extraordinarily stable, and my center of gravity was very, very low. And for the first vehicle that ever had the center of gravity
1933, first minivan, V8 engine,
did prove to be a
22 miles to the gallon. Look at the turning radius.
With 11 passengers, I averaged over 22 miles
Parallel
per gallon.
parking's not a problem with this
30,
thing because it will park sideways, like a little crab.
A front steered car with the kingpins can only steer up to 34 degrees angle. My rear rudder post I could turn so I could give it 90 degrees rudder if I wanted. This meant
see, look at him parking. That's how you parallel park
it. Space just say 6 inches longer than my Dimaxion car. I would simply bring my nose into the curb and then throw my rear wheel sideways, and she went right and flopped like that.
Are we in the future likely to have a great increase in the scientific knowledge, thanks to men from brawn work to do simply brain work?
I see humans around the world having one very, very important function.
That's Buckminster Fuller.
You cannot have mass production unless you have mass consumption.
The future matrix.
The bigger your undertaking. As we really come to automation, which can really do the physical
stuff like
work,
that in '67. He was quite an interesting fellow. All right, let's get back over to the course. I'm not going to apologize for that. I'm a Bucky freak. He had a very bad time in his life when he was younger. He lost a child and was contemplating jumping into the Great Lakes and ending it all. And he decided that there was more to life than what he had right to. And so he got over that depression and went on to be a great inventor. After that, he started working on the Dimaxion car, the geodesic dome, the Dimaxion house, which I said was prefabricated. It would come out on a truck. It had everything in it. Everything. Elon Musk has picked that up with the Elon Musk modular house that he has on the market. You can research that. So let's go on to shell structures. Shells are thin curved plate structures typically constructed of reinforced concrete. They are shaped to transmit applied forces by membrane stresses. Now, It's just like a pipe, a barrel vault or a pipe. Okay. If you take a piece of pipe, you cut it in half. You have these hoop stresses across here. You have the longitudinal resistance of the length of the pipe, but it's also what? It's an arch, is it not? So if you load this too much, what do you have to have down here? You have to have something to resist the forces that want to make it spread out. Okay? And what did we call that? We called that a buttress. Okay, all right, enough of that. They are shaped to transmit an applied force of immense strength. The compressive tensile and shear stresses acting in the plane on their surfaces. A shell can sustain relatively large forces if uniformly applied. Because of its thinness, however, the shell has little bending resistance and is unstable for concentrated loads. What do we mean by concentrated load? Let's say that Godzilla comes over here and steps on it with its big old foot right there in the center. Okay. Well, it's a thin-walled shell. It's just like an egg. An egg can take a lot of external stress if you can uniformly load the eggshell, right? But if you hit the egg on the side of a skillet, what does it do? It crushes the wall of the shell. All right. And it'll start to buckle in this area. And once it buckles, then the whole tensile stresses get all discombobulated. That's a scientific term for them going crazy. And then this thing starts to collapse. All right, barrel shells are cylindrical shell structures. If the length of a barrel shell is 3 or more times its transverse span, it behaves as a deep beam with a curved section spanning in the longitudinal direction. If it is relatively short, it exhibits arch-like action. Tie rods or transverse rigid frames are required to counteract the outward thrust of the arching section. So if it gets too short, it's going to act like an arch because it doesn't have enough room to transmit these forces going that direction. Okay? All right. Again, this is not an engineering course. It's a vocabulary survey course. So don't get all freaked out that I'm going to get all geekizoid. Translational surfaces are generated by sliding a plane curve along a straight line or other plane curve. Now, what in the name of Zeus does that mean? Okay, transitional surfaces are generated by sliding a plane curve along a straight line or another plane curve. What we're talking about here is the hyperbolicness of a shell. Okay, when we start bending this stuff or building it in a hyperbolic manner, and we've got a shell going this way, and we've got an arch here, okay, we have a hyperbolic paraboloid. Suckering succotash is a surface generated by sliding a parabola with a downward curvature along a parabola with an upward curvature, or by sliding a straight line segment with its ends in two skewed lines. It can be considered to be both a translational and a ruled surface. Wow, isn't that special? Now, what does that mean to us? It means it's a curved arc, and your engineers are going to be using a lot of finite element analysis if this is going to be a rigid hyperbolic deal. And thank God we have finite element programs to do this stress analysis. Because in the ancient days of yore, we had to do all this by hand with differential equations and go into finite element analysis by hand. And that's the reason old engineers like me have tendency to wander about between their ears at times. Ruled surfaces are generated by the motion of a straight line. Because of its straight line geometry, a ruled surface is generally easier to form, no kidding, and construct than a rotational or translational surface. Because you have geometry, you have stuff going this way and this way. Whereas here, this is sort of like some of those tents that you've seen, those super funky looking expensive tent structures that people put out on the beach. Okay, so you have this frame here, and you've got a framed here, and everything's in straight lines basically. And the fabric shell just runs across this and that. Okay, whereas this is more gradual, and you've got places for all these stresses to run around if you're not careful when you're designing them. A saddle surface have an upward curvature in one direction and a downward curvature in the perpendicular direction. Definitions. Okay, I'm not going to ask you to get too deep in the weeds on these. In a saddle surface shell structure, regions of downward curvature exhibit arch-like action, while the regions of upward curvature behave as a cable structure. Oh my goodness. If the edges of the surface are not supported, beam behavior may also be present. So what does that mean? If the edges of the surface are not supported, beam behavior may also be present, and we start to what? Sag down. Oh my goodness, sag down. We don't want that. So these are quite a challenge to engineer and design. All right, we already talked about rule surface. All right, this is funny. A one-sheet hyperboloid, not hyperbole, hyperboloid. Oh my goodness, Annie M is a ruled surface. It's a ruled surface like this. It's got lines, stress lines that you can follow. Okay. All right. That spiral around. They're spiraling around. See, spiraling around. By sliding an inclined line segment on two horizontal surfaces. Its vertical sections are hyperbolas. Okay. Now you've seen concrete shells in this shape. I know you have. They're cooling towers. Some of the nuclear power plants have their cooling towers in this shape, and they're concrete shells. All right, a rotational surface are generated by rotating a plane curve about an axis. Spherical, elliptical, and parabolic dome surfaces are examples of rotational surfaces. Now, where have we seen this? Where have we seen this? This is the Sydney Opera House. The Sydney Opera House in Sydney, Australia. Look at this. What are these? These are folded. These are shells. This is a shell structure. Shell structure. Look at that. I'll have a PowerPoint. You'll just have to ignore the advertisement on the PowerPoint thing on shell structures for your purview. But these are plates. What kind of plates are these? What kind of plates are these? Would that not be more of a ruled surface? A ruled surface? That's how it was engineered. Okay. All right. And some of them are rotational surfaces. So they've combined these things. All right. And they've combined these things. Now, cable structures. Cable structures. Let's see if I can get this over here for us to utilize. There we go. These are cable structures by a German architect by the name of Frei Otto. There's one there. It's a 2020 event. Here's past events. Let me pull this one up. This is the World Architecture Community one. Let's see. Yeah. This is the Alvalor Alto Academy lecture by Fry Otto, um, and this is a cable structure. I'm sure you've seen these around at various places. Fry Otto pioneered the mathematical design and the engineering of these. These things will cover a lot of area. Obviously, they don't do a lot for heating and air conditioning. So what do you do inside? Then you have to build small little environmental structures inside these things for the shops and that sort of thing. But this covers a lot of area so that the structures underneath that need HVAC do not have to be as strong as if it was a conventional single building like a shopping mall would be. Let's see here. Let's pick one more and then we'll move on. Does that not look familiar? This is a fabric or cable structure, but it is what? Looks like a ruled surface, does it not? It just happens to be a tent. And when you design that, you would design it as a ruled surface. Does that make sense? That's all part of cable structures. Some of them can be folded, double curvatured. Cable structures have guy cables to absorb the horizontal component of the thrust and a suspension cable. Well, you can read all this. I'm not going to read this line by line. Let's see. There was something in here I wanted to point out. Just like a bridge, you got suspension cables and columns. And these are the force vectors of how all this works. Again, this is not a statics course, so don't get freaked out. You're not going to be asked to analyze this stuff. You have single curvature, you have double cabled, and you have multiple curvature. We saw the multiple curvatures over here. Well, wow, this is not going well, is it? There we go. This is a multiple curvature tensile structure by Fry Otto. I studied a lot of his work when I was in college. All right. This is a double curvature. We've got a curvature here, curvature there. Cable stage structures. Some space frames. This would be the space frame. Remember we talked about space frame. It would cover a large area. Maybe this is a giant arena out here and we don't want columns there, so we have two columns, and we will use cables to support the space frame, right? To hold it up. Okay, membrane structures is just what we looked at with Fry Otto. All right, membrane structures. All right, it's a cable structure or thin flexible surfaces that carry loads, but they're also supported by cables and columns. Okay, what's the difference between a cable structure and a membrane structure? Cable structures utilize the cable as a principal means of support. Well, membrane structure is the principal means of support. That piece of fabric's not going to support it. We got cable. So this is a blending of cable structures and membrane structures. And just like a tent, you got tent poles. They can be as big as those giant ones that you saw in that Fry Otto photograph. Let's see. Structures that are pre-stressed. You can read this. It's not a big deal. Okay, these are flexible structures. We have pneumatic structures. Okay, now I talked about the airform in the Monolithic Dome Institute, right? All right, what they do, it's a giant airform balloon basically in the shape of the dome. It's custom made to, that's your form. And it's like in any concrete forming, your form work is a high dollar item, but it's got to be done right. So an air structure or pneumatic structure, they're a membrane structure that are placed in tension and stabilized against wind and snow loads by the pressure of compressed air. The membrane is usually woven textile or glass fiber fabric coated with a synthetic material such as silicone. They can be translucent to provide natural illumination. There are two kinds of pneumatic structures. There's air supported and air inflated. Now, obviously, the air inflated is like an air mattress, right? Okay, and air supported structures. So, an air supported structure consists of a single membrane supported by an internal air pressure slightly higher than normal atmospheric pressure and securely anchored and sealed along the perimeter to prevent leaking. Airlocks are required at the entrances to maintain the inertial air pressure. All right. That's what the airforms are for the Monolithic Dome Institute. You have a big fan on the outside. There's an airlock that's built into the form, and it's usually where the front door will eventually go. And it blows it up in its shape under a few inches of water or pressure, and then you spray the foam on the inside. That foam hardens. You've already got your anchors embedded in the foam for the rebar. You spray the next layer of foam, and then tie the rebar with a space, and then you come in with the shotcrete and blow the shotcrete, which is gunite. Actually, gunite's a little finer than shotcrete, but it's the same thing. It's pneumatically sprayed concrete, just like you do for a swimming pool. All right, air-inflated structures are supported by pressurized air within inflated building elements. These elements are shaped to carry loads in a traditional manner while the enclosed volume of the building air remains at normal atmospheric pressure. So in other words, an air-supported structure has got a sealed air bladder in there that you inflate like an air mattress. So if you just took like an air mattress and bent it into an arch, that would be an air-inflated structure. I mean, yeah, an air-inflated structure. Yeah, trust me, I'm the instructor, right? Now, what do you think if this is an arch and you're going to have loads on it? You're still going to have the same forces that an arch has, right? You'll still need some kind of buttressing out here and tie down, and then some compressive loading. So that means this has to resist that coming back up like that. Okay, and so, but for an air supported structure where this is sealed, all right, you got a resultant force here and a force there, so you need a buttress out here too, because it's still an arch. I don't care, even if it's circular. It's like the geodesic dome. It's round. Well, that's sort of round. Pretend it's round, okay? And you've got these tensile forces at the bottom that's going around the circumference of it, and you also have outward forces because it's trying to squish out, okay? But not as bad as a singular arch or barrel because it's circular. All right, so I think you have an idea of, and you can spend the rest of your life in different kind of structure. I'm using dome. I love things. I love domes, even though they pose challenge for interior decorating and laying out interior spaces. And they don't fit with the normal architecture in a urban environment. You take a typical subdivision lot, like I said, and try to put one of those on it, you're going to have some problems, some real problems. So there are other areas of avenue for precast and for rectangular buildings. The Elon Musk house is one. It's a rectilinear shaped structure, which would fit more into the normal subdivision environment. All right, joints and connections. What do you think might come out of here? Maybe some test questions. You could. This could be a test sheet, right? So let's look at these. Butt joints. It means just what they are. They butt up. Okay? Interlocking or overlapping joints. Molded or shaped joints. This would be like one of those old barns, heavy wood construction like the Amish might build. Problem with butt joints would be what? Depending on what material you're using. I mean, if this was wood and that was wood, how are you going to butt it up and stick it in there? Are you going to toenail it? Not if it's my building. I'm not going to let you toenail it. You're going to have to come up with some kind of joint detail to secure all of that. Here we have a point connector joint. And this talks about all the forces in which these things are put together. The butt joints are a pin connection, okay? And require a third mediating element to make the connection, right? This is a challenge. Point connector joints where it's a bolted through, all right? If this is all that you're doing, then this can rotate. It doesn't make a very strong frame, but it's good. It's better in shear, right? Okay. Now they make all kinds of connector plates that go with the butt joints. I know that. Okay. Angle plates down, angle plates up, and you nail into this and nail into that. It would be an angle plate up. Okay. And that would secure it. Okay. And they also make stuff that can clamp. You nail into the column, and then the horizontal beam fits into that metal clip plate. Sure Tie makes these, and then you nail into the side, and it makes a more secure deal. So when you doing your framing, you need to decide how you're going to do this. Here's a linear connector weld, or a welded joint. It's only fillet welded at the top. Okay. So it'd be fillet welded across the top here and fillet welded along the bottom. This is not a moment connection. If you wanted to make a moment connection, you would need to weld all the way around. You use this symbol here for all the way around welding now. And you would have to weld all the way up underneath here and there and there and watch your heat affected zone so you don't overcook your steel. And that would make that more of a rigid connection. But if you're going to transmit the rotation from the column, from the beam, then we would have to come in here and put a moment transfer plate. Oh man, I'm really screwing this drawing up, aren't I? A moment transfer plate in here, and then you would have to weld all the way around here on the back side of that flange. And at the top, you'd have to do the same thing down here. That would disappear. One boogering this up, aren't I? Do not do drafting the way I'm drawing. Okay? All right. Now you could transfer all the rotation from the beam to the column, and that would be a true moment connection. All right, I digress. All right. Read all of this. Read all of this. Okay. Bolted connections. This is more of the tie plates that I was talking about. Precast concrete connections. This is a clip pad on a corbel. This is called a corbel in concrete world, and it's cast in with the column, and you set the beam on that. And if this was a concrete beam, there would be a pin underneath there. If it's wood and it's going to a concrete column, let's say this was a laminated engineered structural wooden beam because you want it to look cool. It's laminated. We'll put some laminated lines in there. Then this plate would come up even higher, and you would lag bolt it, screw it, and do some structural screwing on that. This is still a pin connection. It'll allow rotation around the joint. This is showing, though, an isolation pad. An isolation pad. So the way this is joined, it's allowing this to be isolated from being a rigid connection. So if it's just set in on a clip and it's not welded, like in precast concrete connections are often welded, they'll have embedded steel plates on the beam and the corbel, and then you would have a welder come up there and then do a weld on both sides to hold it in place. But if this is not welded, which there are no weld symbols on this, then this would allow this to slide back and forth, and hopefully not slide off the corbel and fall down and go boom. But if it's a typical precast concrete structure, these connector plates would be cast with the elements, and then once they're set and squared up, and the construction engineer gives the okay that it's square and plumb. Plumb is vertical, up and down. Level is this way. Well, not quite like my line. And this is square. All right, it's square. Square. Okay. Well, pretend that's the square symbol. You would come in here and you would weld around this at the bottom, and it would be connected. All right, pin joints are theoretically allow rotation, but resist translation in any direction. So it allows it to rotate, just like a hinge on a cabinet door. All right, but it won't let it move this way or that way. It's pinned. Okay. All right. Welded steel connectors. Well, looky here. This is a true moment connection. Okay. I did all this monkey motion up here. Y'all are laughing, I know. I can see you in the first row laughing at me. Oh, this is a lecture for online, so it's my imaginary friends now laughing at me. But anyway, this is supposed to be a moment connection, although you would still weld across here. All right. So this allows full transmission of the forces across here. It has full resistance for shear going this way. Remember, shear is like a set of scissor blades. Obviously, I'm not any kind of words. Okay. So you have a vertical force going across, and it's shearing the material in between the two lines of force. All right. And it allows for full rotation resistance. Let it rotate, it gives rotation resistance. So if this is bending this way, let's say this is bending down that way, or it wants to bend down that way, then this will go the other way to resist it. The column will take that moment and transmit that force down to the foundation. Okay. Now, this is cast in place reinforced concrete. Now, as a structural engineer, I'm going to take exception to this detail. Let's assume this is the column, and this to me is a suicide connection in structural engineering. All right, but the idea here would be that you would form up another beam and then cast that beam across there, leaving you a construction joint in the moment region of this fixed frame, and that's a bad thing. So in reality, to make that right, you would kill your column here. Your column would come up, all your columns would come up to that elevation. You would have the reinforcing steel still coming through, hopefully better than that. You would have a keyway, a construction point here. Then you would come in and cast your beam, your concrete beam, at that construction joint, leaving the rebar coming up through the top of the beam. And then when this concrete reached its minimum of 7-day strength, minimum of 7-day, preferably 14-day, then we'd come in and frame up the rest of our columns, and carry on the building that way. I don't know why they detailed that way, but anyway, over here we have a cable anchor. It allows rotation but resists translation only in the direction of the cable. In other words, if this was one of those cables for one of those membrane structures, then of course, the tent's going to pull on that, and that'll keep it from moving that direction. But when the wind blows, it's going to allow some kind of rotation, right? It'll allow it to pick up and move around. All right. This is a lap bolted joint. That's not very structural, as you can see. But that would be called a lap joint. If you wanted it structural, then you would have to, rule of thumb is 1.5 to 2 times the depth of a lap, and then seriously screw or nail or bolt that connection with more than one fastener. 1.5 to 2 times the depth, if you wanted that to be a structural deal. Let's see, and they have mechanical plates that help with that too. They have lap plates, like pressed metal plates like this, that one piece of the wood would be on that side, and then you nail that in place. You put the other piece of wood, the lap, in here at the proper distance that the manufacturer recommends to transmit the load, and then you would then through bolt the thing. All right, roller joints. They allow rotation but resist translation. All right, in other words, they resist being moved up or down if they're a captured roller joint. But let's say this was a bridge deck, and we wanted that roller for expansion. And sometimes you'll see a bridge deck with something very similar to this, okay, where the bridge girder comes across, the road deck comes across, and or the bridge deck, and on the foundation you would have something like that, and something like that. You can see these on some structural steel road bridges if you go into the underpass. Something like that. Keeps it from moving up and down, but it allows for rotation. Now what it won't do, what this true pin connection won't do, it won't allow for expansion. If this was captured to keep the thing from being lifted up by Godzilla, this would allow also for what? A certain degree of expansive movement. It could roll that way. And of course this would not be concrete, this would be a steel rub plate. It could be captured. So there are all kinds of connections and joints. So joints and connections. I think we've probably beat this. Oh yeah, we're at 49 minutes. Wow. So study this. This ends chapter 2, and we'll move on into chapter 3. So we'll see you on the next set of videos.